Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is Kirchhoffs' voltage law. Our objective today is to develop an understanding of Kirchhoffs' voltage law and use it to analyze, verify calculations, and troubleshoot simple series DC circuits. Primitive man's observation of the simple fact that what goes up must come down belies the importance of such a seemingly no-duh statement. Prior to the acceptance of this idea, there were probably a lot more spear injuries than there are today. We can extrapolate this simple statement to a number of different far-reaching conclusions, including the birth, expansion, and inevitable contraction and death of our own universe. But the German scientist Gustav Kirchhoff, in the mid-1800s, was the first to apply such a concept to electrical circuits. The simple statement of what goes up must come down is reworded in Kirchhoff's memorable observation that the algebraic summation of the potential rises and drops around a closed path is zero. It may help to rephrase this ever so slightly and state that for any given loop, the sum of voltage rises equals the sum of voltage drops. What goes up must come down. A key concept to this idea is that of a loop, a path, or a circuit, meaning you come back to where you start, having traveled a circle, a square, a triangle, a rectangle, or any shape with a closed perimeter. There are smart and easy places to start a loop, and there are dumb and hard places to start a loop. But regardless of where you start, you should return exactly where you started once the journey is complete. In addition to your choice of starting point, you can choose any direction to travel. The same caveats apply. You can go in the outdoor and up the stairs clearly marked down, but that would be dumb and hard. Keep in mind we'll be applying Kirchhoff's voltage law to very simple series DC circuits in this lecture, meaning those that have only one path in the first place. But be aware that Kirchhoff's voltage law can be applied to even the most complicated of circuits, including those that have numerous different paths within them. For any single loop, the sum of voltage rises will always equal the sum of voltage drops. We'll be referring to Kirchhoff's voltage law by its initials KVL. You often hear me refer to it as if it was a verb, as in the phrase KVL it, meaning perform a detailed Kirchhoff's voltage law analysis and you will arrive at the answer you seek. In addition to it being used as an active verb, you can think of KVL as exactly what the name implies, a law. If you break the law, you go to Kirchhoff's jail. If the idea of pumping iron with a bunch of swarthy men and making license plates all day doesn't appeal to you, operate within the confines of KVL and simply obey the law. Outside of a direct analysis technique, KVL additionally makes a great method of sanity checking your work to see if the results make sense. Those results outside the law are rounded up and punished or rehabbed accordingly. Algebraic summation is just a $10 word that means pay attention to the sign as you travel your path. If you go in a negative sign and come out a positive, it's like going to work broke and coming out with a fat paycheck. Your net worth has risen. If you go in a positive and come out a negative, it's like walking into Vegas with a fat paycheck and leaving it with empty pockets. Your net worth has fallen. This is why I prefer the rephrased Kirchhoff's voltage law. For any given path, the sum of voltage rises equals the sum of voltage drops. In this simple two-element series circuit, the Kirchhoff's voltage law equation is E equals V1 plus V2. For any given path, the sum of voltage rises equals the sum of voltage drops. Pick one side of the equation to represent rises. The opposite side is reserved for drops. Along the way, you might find unknown voltage drops or rises, but with a little thought and effort, you should be able to manipulate your first draft to arrive at the answer you seek. We'll begin with an illustrated example of a Kirchhoff's voltage law analysis of this simple series DC circuit consisting of two resistors in series with a single source employing a ground reference. Let's review our basic properties of series circuits and spend some time discussing voltage distribution within this closed path using Ohm's law. The first and most basic property of series circuits is that current through elements hooked in series is the same. Therefore, it can be said that IS, the source current, is equal to the current going through element 1, I1, and also equal to the current going through element 2, I2. IS equals I1 equals I2. The source current is equal to the supply voltage divided by total resistance, where total resistance is the summation of resistance in this path, where RT is equal to R1 plus R2. Therefore, source current is equal to E divided by RT. The voltage drop across resistor 1 is the current through it times its resistance, V1 equals I1 times R1, and the voltage drop across resistor 2 is the current through it times its resistance, V2 equals I2 times R2. If this two resistor series combination is idealized as a single resistance RT, it is readily apparent that the voltage drop across RT, which I'll call for a lack of a better term V, is obviously equal in magnitude to that of the rise E. It stands to conjecture that R1 and R2, those resistors that compose RT, drop representative portions of this applied voltage. Using our single resistor simplification, it can be stated that the voltage drop across RT is the source current times the total resistance. E equals V equals IS times RT. Using our series resistance formula, where RT equals R1 plus R2, this formula can be rewritten as follows. Distributing IS into the parentheses, we find IS times R1 plus IS times R2. Understanding the most fundamental aspect of series circuits is that current through elements in series is the same. Because IS equals I1 equals I2, I can rewrite this as I1 R1 plus I2 R2. Using our understanding of Ohm's law, we realize that I1 R1 is V1 and I2 R2 is V2. It can be stated that E, our voltage rise, equals the summation of our voltage drops, V1 and V2. This is Kirchhoffs' voltage law derived using Ohm's law. For this circuit, it can be stated that E equals V1 plus V2. We can arrive at these same results using different methodology. This alternative method is simple, quick, and importantly, just as correct and valid as proof of this concept demonstrated using Ohm's law. We'll start by KVLing it the smart and easy way, then once we're done, we'll KVL it the dumb and hard way. Regardless of the manner of our analysis, we'll prove our circuit is a law-abiding member of society and conforms to KVL. First, if the circuit has a ground or a point of reference, start here. To start any other place is dumb. Second, if the circuit has a single source, or a single source that clearly overwhelms other sources, we'll get to that one in a little bit, travel in the direction of induced conventional current. To travel in any other direction would be hard. Our example circuit has a ground reference and clearly induces current in the clockwise direction. This is the smart place to start, and this is the easy way to go. Conventional current induces voltage drops across our elements with the indicated polarity. Leaving ground, we enter the negative terminal of our source and come out the positive. This is a voltage rise of the value E. This goes on one side of the equation. Leaving the positive terminal of the source, we enter the positive terminal of resistor 1 and leave its negative terminal. This is a drop of V1. A drop goes on the other side of the equation. Leaving the negative terminal of resistor 1, we enter the positive terminal of resistor 2 and leave its negative terminal. This is a drop of V2. A drop goes on the other side of the equation. The KVL equation for our circuit is E equals V1 plus V2. Notice at no point did I have to resort to any messy derivations using Ohm's law or any series circuit properties. Additionally, notice we arrived at the same results. E equals V1 plus V2. The sum of rises equals the sum of drops. This should have been very easy to understand, and we'll return to an extremely powerful application of these results in a second. I've yet to prove to you that you can KVL things the dumb and hard way and still get the same results. Let's start here. This would be dumb. And just to be obstinate, let's go in this direction, counter to the flow of conventional current. This would be hard. And away we go. Leaving our poor choice of starting points, we enter the negative terminal of resistor 1 and come out the positive. This is a rise of the value V1. This goes on one side of the equation. Whoa, wait a second, some of y'all might be saying. I thought passive elements like resistors are voltage drops, not voltage rises. Yeah, that is true if we're doing it smart and easy. But we're doing it dumb and hard just trying to prove a point. When you travel in this direction, you're going in a negative and coming out a positive. So V1 is now considered a voltage rise. Moving on, leaving the positive terminal of our resistor, we enter the positive terminal of the source and leave its negative terminal. This is a drop of E. A drop goes on the other side of the equation. Leaving the negative terminal of the source, we enter the negative terminal of resistor 2 and leave its positive terminal. This is a rise of V2. A rise goes on the other side of the equation. The KVL equation for our circuit is V1 plus V2 equals E. Oh my gosh, it's the exact same equation we arrived at when we performed the Ohm's law derivation and the KVL analysis the smart and easy way. Let this be a small comfort to those individuals in life that are consistently wrong. Even stop clocks are correct twice a day. Smart and easy and dumb and hard yielded the same results. The point is we were consistent and never switched directions or ended at a place different than where we started. Start anywhere and go in any direction you wish. Come back to where you start. Positive to negative is a drop and goes on one side of the equation. Negative to positive is a rise and it goes on the other side of the equation. Now that I've demonstrated the quick and dirty KVL method, let's apply our results. Understanding the sum of rises equals the sum of drops, we can use this understanding in two manners. Number one, we can check our Ohm's law calculations. Number two, and this is where it gets especially interesting, we don't have to do Ohm's law calculations. Allow me to demonstrate. Consider the same two resistor series network where the supply is 7 volts. Resistor 1 is 130 ohms and resistor 2 is 220 ohms. Our total resistance is R1 plus R2, 130 ohms plus 220 ohms, yields 350 ohms. A 7-volt source, opposed by 350 ohms of total resistance, would induce a source current, IS, of E divided by RT, 7 volts divided by 350 ohms, or 20 milliamperes. If 20 milliamperes traveled through resistor 1, we could easily determine the voltage drop using Ohm's law, where V1 equals I1 times R1. 20 milliamperes times 130 ohms yields 2.6 volts. Now, what's the voltage drop across resistor 2? Here's the important part. Without using Ohm's law. Use Kirchhoffs' voltage law. Pause the lecture and take your best shot at this. We need to perform an analysis of the voltage rises and drops for this series loop. We previously demonstrated this circuit should exhibit a rise of E on one side of the equation, a drop of V1 on the other side of the equation, and another drop of V2. Now all we have to do is put some numbers in there. E was given to be 7 volts. V1 we calculated using Ohm's law to be 2.6 volts. Now solve for V2. Subtracting 2.6 volts from both sides means V2 must be 4.4 volts. Mathematically, this should make sense. More importantly, electrically, this should make sense. If we start at ground and go up 7 volts, and then fall 2.6 volts, where are we with reference to ground? The answer is we are still 4.4 volts higher than ground and we must fall 4.4 volts to return to ground. Makes sense. Now check your work. Does Ohm's law agree with your KVL analysis? Using the Ohm's law, the voltage drop across resistor 2 is the current through it times its resistance. 20 milliamperes times 220 ohms yields a 4.4 volt drop. Ohm's law agrees with KVL. Just to make sure, does KVL agree with our earlier calculations of V1 using Ohm's law? In this case, 7 equals V1 plus 4.4 volts. Subtracting 4.4 volts from both sides, oh my gosh, V1 is equal to 2.6 volts, just like we calculated earlier. Finally, does the sum of voltage drops calculated via Ohm's law really equal the rise? Yes, indeed it does. 2.6 volts plus 4.4 volts is indeed 7 volts. I've got this sneaky suspicion we might be right. Not only is KVL the chicken before the egg, before the chicken and before the egg, and so on, it's also the spare tire, the backup parachute, a handy roll of hidden cash, and a readily accessible handgun. KVL is the method you use again and again to prove things are right, and the backup plan you can always rely on in case things go wrong. If at any point we incorrectly performed any step, our KVL analysis wouldn't work out, and we could track down the source of our problems and rectify or rehab those results that need it. For example, let's say we totally dorked up the first step of the problem and just added numbers wrong. 130 ohms plus 220 ohms equals 360 ohms. Don't laugh, it happens. With a 7-volt source and 360 ohms of total resistance, we would anticipate close to 19.4 milliamperes of current traveling through our circuit. Wrong total resistance means wrong source current. With 19.4 milliamperes of current traveling through a 130 ohm resistor, we would anticipate a voltage drop of close to 2.53 volts. Wrong total resistance yielded wrong source current, yielded wrong voltage drop. Can you see how things are already starting to snowball? With 19.4 milliamperes of current traveling through a 220 ohm resistor, we could expect approximately 4.28 volt drop across it. Again, another wrong voltage drop. Does our voltage rise equal the sum of voltage drops? No, 6.8 volts does not equal 7 volts. We are no longer on the path of righteousness, and we are keenly aware of it. What if we went about this in a different manner, though? Let's say we calculated the voltage drop across V1 using our wrong source current, and then just jumped to KVL. V2 should be equal to approximately 4.47 volts. But it isn't. How do we know it isn't? Ohm's law is now used to check KVL. Even using our incorrect source current is not in agreement with our KVL analysis. Again, we are keenly aware that something is wrong because the results are not in agreement with another. That's the point of KVL. Not only can it be used as a substitute for Ohm's law, it can be used to check Ohm's law. And wrapping back to previously covered material, Ohm's law can be used to check KVL. The important point is that both methods should agree, and they should both be correct. The choice is yours. Choose wisely, though, because although the different methods yield the same results, a given method might yield correct results quicker. Only familiarity with both Ohm's law and KVL will allow you to differentiate between these finer aspects. Beyond its ability to be used as a substitute or check to Ohm's law, one of the greatest and most powerful applications of KVL is its use in real-world measurement and troubleshooting scenarios. Without having to solve for current, without having to solve for voltage, without having to solve for total resistance or any other make-work stumbling blocks, with a known voltage source and a single voltage reading across any single element in a 2-element series network, you instantly and quickly and reliably know the voltage drop across the other element using a simple restatement of KVL. Calculations aside, if you took your voltmeter in DC voltmeter mode and measured the voltage drop across the first resistor, even if the resistor value was unknown and the resistor color code somehow obscured or unreadable to be 2.6 volts, you could be reasonably certain that the remaining 4.4 volts is dropped across the second resistor. Let's try a couple more illustrated example problems applied to simple series DC circuits. Consider this two resistor series network with measured voltage drops of the indicated polarity across unknown resistive elements and an unknown supply voltage. In this case, there is no ground reference. Lacking a ground reference is of no concern because we can clearly see that node A is 30 volts higher than node B, and node B is 18 volts higher than node C. A ground reference means exactly that. The voltages are simply referenced from ground. It's just a reference, and it is not essential to the functionality of this closed circuit. Node B is still 18 volts higher than C. Node C, for all intents and purposes, could be 5,000 volts or 5 kilovolts higher than ground. Node B in this case would still be 18 volts higher or 5,018 volts referenced from ground. The point being, this circuit is a loop around which KVL can be applied. We can pick any point in our network. Here is my preferred starting point, and travel in any direction we wish. Obviously, going in the direction of conventional current is the most logical choice. This is the smart and easy way to go. When we travel this direction, we go negative to positive through our source, meaning this is a rise of the unknown value E and goes on the left-hand side of the equation. Now we travel through element 1, positive to negative for a drop of 30 volts, and it goes on the right-hand side of the equation. Finally, we travel through element 2, positive to negative, for a drop of 18 volts, which goes on the right-hand side of the equation. We quickly and easily realize that E is a 48-volt source and must be oriented in the following fashion to induce a voltage drop across element 1 and 2 with the indicated polarity. Now, let's add a ground reference node to this circuit and see if this in any way affects the functionality or KVL analysis of this circuit. Some of you may be groaning and slapping your forehead, saying that's not where I expected the ground reference to go. This placement of the ground reference on the positive terminal is of no concern to you. A circuit still exists and KVL can still be applied. Starting at ground, we travel through element 1, positive to negative, for a drop of 30 volts, which goes on the right-hand side of our equation. Then we travel through element 2, positive to negative, for a drop of 18 volts, and it goes on the right-hand side of the equation. Now we continue our loop. We go negative to positive through our source, meaning this is a rise of the unknown value E, and goes on the left-hand side of the equation. E is again 48 volts. A 48-volt differential still exists, and conventional current will still travel in the indicated direction. The only relevant piece of information this new ground reference carries is that the negative terminal is simply 48 volts lower than ground. If you wanted a means of visualizing this, start at ground, drop 30 volts, then drop an additional 18 volts. This is in contrast to a ground reference on the negative terminal of our supply. Starting at our new ground reference on the negative terminal and traveling in this direction, we rise our unknown value E, then drop 30 volts, then drop an additional 18 volts. It can again be stated that our source is providing a 48-volt rise. The only difference between this and our other circuits is that this is now referenced from ground, and the positive terminal is now 48 volts higher than ground. A 48-volt differential still exists, and conventional current will travel in the clockwise direction. If you want a means of visualizing this, start at ground. Go up 48 volts. Now that we've got some salt in a wound, let's vigorously rub that wound by placing a ground reference at node B. What, in its most basic terms, this ground reference is implying is that node A is still 30 volts higher than ground, And this same ground node is 18 volts higher than node C. Equally as valid is the statement that node C is 18 volts less than ground. If you wanted a means of visualizing this, start at ground. Go up 30 volts to get to node A. Go down 18 volts to get to node C. How is this 48 volt differential established? Quite obviously via a 48 volt rise, and we can use KVL to verify this. Starting at ground, we drop 18 volts. Rise our unknown quantity E, and then drop 30 volts. Our source is still 48 volts, and conventional current will still travel in the clockwise direction and induce a voltage drop across our two elements with the indicated polarity. In all these cases, a 48 volt differential exists, only this time is referenced on one side, the other, or both of ground. Some of you may be frustrated to no end because I've been seemingly flip-flopping between calling the voltage differential across a resistor a drop on one hand and a rise on the other, especially when I'm employing the dumb and hard methodology. You'll be happy to know that this distinction is of no concern as long as you're consistent. Traveling negative to positive means a rise. Traveling positive to negative means a drop. The sum of voltage rises always equals the sum of voltage drops. No situation is this more prevalent than the unknown element problem. It doesn't matter if an unknown element is designated a passive element or an active source. The sum of voltage rises will always equal the sum of voltage drops. In this particular example, we've got 4 unknown elements in a series relationship, 3 of which the voltage drops, or rises, since it's not clearly indicated, are known. One of the elements has an unknown voltage gradient across it, and additionally, it has an unknown voltage polarity across it. In a situation such as this, you can just pick a starting point and direction of travel randomly. Because as we previously demonstrated, it doesn't matter if you're right. It just matters that you're consistent. Additionally, you can just randomly assign a polarity to the unknown element. If you get a positive answer, it means you randomly chose the correct polarity. If you get a negative answer, it means your magnitude is correct, but you just randomly chose the wrong polarity. It'd be really easy to fix it by putting a negative where you put the positive and a positive where you put the negative. Let's just start here, and keeping with tradition, travel clockwise through our loop. Keep in mind, I have no idea what these elements are. They could be active sources, passive elements like resistors, or for that matter, just cool-looking boxes stuffed with dead leaves. I don't know what they are, and I don't care what they are. The sum of voltage rises will always equal the sum of voltage drops. Traveling in the clockwise direction, we go negative to positive, which means V4 is a voltage rise and goes on the left-hand side of our equation. Now we go positive to negative through V1, which means it's a voltage drop, and it goes on the other side of our equation. Now we go plus to minus through V2, which means it is also a voltage drop, and it must go on the right-hand side of our equation. Finally, we hit unknown element 3 with an unknown polarity. Let's just assume it has polarity positive to negative and is therefore considered a voltage drop, and it would go on the right-hand side of our equation. If we are correct in this assumption, we should get that same polarity. If we are wrong, we'll get a negative value. The magnitude in both cases would be the same. Substituting in the given values, we find that 18 volts equals 24 volts plus 12 volts plus V3. Subtracting 36 from both sides yields V3 as negative 18 volts. This negative value needn't be surprising given the polarity we randomly assigned it. If you think about this, this means from this positive polarity marker, we've dropped negative 18 volts to get to this negative polarity marker. A drop of negative 18 volts with the indicated polarity is in actuality positive 18 volts with the indicated polarity. Traveling in this direction, it would be an 18 volt rise. Long story short, we just chose our polarity incorrect. Let's just get rid of our initial assumptions and put in the proper polarity markers and voltage magnitude. Let's verify this by redoing our Kirchhoffs voltage law analysis and randomly assigning the unknown element V3 with polarity markers positive to negative left to right. This again should yield the same result of V3 having a magnitude of 18 volts, only this time we initially happen to choose the correct polarity. Let's pretend we don't know it's 18 volts and do our KVL analysis to see if we're correct. Using the same starting point and traveling in the same direction, we go negative to positive through V4, which means this is a rise of 18 volts. Now we go positive to negative through V1, which means it's a drop of 24 volts. Then positive to negative through V2, which means it's a drop of 12 volts. And finally we go negative to positive through V3, which means it's a rise. Subtracting 18 volts from both sides yields V3 equals positive 18 volts. The magnitude is the same, only positive, meaning this polarity assumption is correct. What is V3? Is it an active source? Is it a passive element? Is it a box stuffed full of dead leaves? I don't know. I don't care. It has a voltage gradient of 18 volts across it with the indicated polarity, and Kirchhoffs voltage law holds true. If in fact V3 was an active source, it would also mean V4 was an active source, and V1 and V2 are passive elements. This is our first real look at circuits with multiple sources. Multiple source networks needn't be confusing because regardless of their numbers or orientation, Kirchhoffs voltage law holds true. The sum of voltage rises always equals the sum of drops for any loop. Here is a circuit with two DC sources that, considering their polarity, if left to their own devices, would both be causing conventional current to flow in the same clockwise direction. They seem to be working together or aiding each other. Appropriately enough, this is known as a series aiding configuration. There are all sorts of tricky ways to draw a series aiding configuration, but the most basic and easily recognizable one is where one DC source's positive terminal is hooked to another source's negative terminal in a continuing chain, and then the last positive terminal is connected back to the original negative terminal via an electrical load or loads. If both these sources were 6-volt batteries, then considering the ground reference is hooked to E1's negative terminal, E1's positive terminal is 6 volts higher than ground. From this new 6-volt reference, E2's positive terminal just brings it up another 6 volts. Where are we now with reference to ground? We are obviously 12 volts higher than ground. Sources in series aiding configurations add up. Our adjustable load resistor now experiences a 12-volt drop. You may have previously seen a configuration like this, for example on a recreational vehicle with two 6-volt deep cycle batteries hooked in a series configuration to produce 12 volts to run adjustable loads like some DC lights, water pumps, or a refrigerator. Another example of a series aiding configuration of multiple sources is a string of 96 3.7 volt lithium ion batteries. This is being one of the 3 parallel strings of batteries in the original Chevy Volt. Don't worry about the 2 other parallel strings of batteries just yet, but realize, quite like our measly little 12-volt RV example, we just keep stacking references on top of each other like 3.7-volt tall acrobats at a circus. With reference to ground, the first battery's positive terminal is 3.7 volts higher. When the next battery's negative terminal is at this same voltage, its positive terminal is still only 3.7 volts higher than its negative terminal. But because of the series aiding configuration, it is now 7.4 volts higher than ground. Now, do this 96 times to come up with a string voltage of 96 times 3.7 volts, or 355.2 volts. Lest you think these series aiding configurations be confined to the automotive world, consider a photovoltaic array. where at certain illumination conditions, each solar panel can be ideally modeled as an identical DC voltage source. Let's say we've got 15 PV panels, each panel having an output voltage of 31 volts. To hook up a series aiding string of PV panels, take the first one's positive terminal and hook it to the next one's negative terminal, and continue in this fashion throughout the array. The modules themselves need not physically be placed in line with one another. As long as they are electrically in series with one another, this will be a series aiding configuration. This string of 15 panels, each producing 31 volts, would have 15 times 31, or 465 volts DC across it. 465 volts. This is the reason why you want to keep your PV wires out of reach of neighborhood squirrels and tweakers. Provided these PV wires aren't squirrel gnawed or clipped off and sold to a scrap metal vendor, this 465 volt DC input can now be fed to a grid interactive inverter. An inverter, if you recall, is a power electronics device that converts DC to AC. In this case, grid compliant AC, with proper magnitude, frequency, and phase shift, suitable for export to the grid. We'll return to solar power, AC, and power electronics devices like inverters in much later lectures. However, despite the high-tech nature and application of these circuits, they're really just simple series aiding configurations, just begging you to bust out KVL on them. A quick note about these series aiding configurations before we continue though. Let's say one of those 96 batteries in the Chevy Volt suddenly loses a connection, or one of the neighborhood kids tosses a large opaque frisbee onto your roof, and it perfectly covers up one of the solar panels. Trust me, it's a really big rectangular shaped frisbee. All the other solar panels are exposed to sunlight and ready to rock, except the one panel in the dark. Let's keep it simple and say this darkened panel's resistance increases to infinity, or becomes an open circuit condition and current through it ceases. What happens to the current in the whole series string? Aha! Current through elements in series is the same. There is no current through this one panel. There is no current being exported by this entire series string. My advice is to buy every kid in your neighborhood small see-through frisbees. What about this configuration right here? This is one of those idiotic example problems you often see in basic electronics textbooks. It's supposed to challenge your KVL skills, but all it does is piss you off because you spend time wondering what on earth it's supposed to represent. I try to stay away from these types of problems, not because I'm softballing you, but because I have no idea what it's supposed to represent. I'm trying to apply all these basic electronics principles like KVL to circuits you're really going to see and really work on, not these made-up monstrosities that look like they dove into a parts bin covered in glue and crawled back out. To top it off, the textbook typically has the wrong answer in the back. Still, this is just a simple KVL problem, and if you look at it correctly, you'll find it's a series aiding configuration. It may help to redraw this monstrosity in a more reasonable fashion. The only rule in redrawing schematics is don't make hard problems harder. You can't change connections, but you can make them easier to comprehend. I could shift R1 and R2 to make something at least recognizable as a closed loop. Now I can redraw this common point of connection, being one terminal of R2, the negative terminal of E1, and the negative terminal of E3, and the positive terminal of E4 as a single node. Because I'm going to need some space for my calculations, I'm going to shift E3 over a little bit too. Now I can place some nodes in there, and then give them identifiers. Notice this is now a much easier circuit to apply KVL. I still have no idea what it does, but it's not nearly as confusing. We're being asked to find is the voltage drop across R1 and R2, being V1 and V2, as well as the two other independent voltage drops, VAE and VCF, with the indicated polarities. What we really got here is several independent loops, only one of which actually includes a complete circuit. My advice is to go after one loop at a time. The first and most obvious loop is that formed by E1, R1, E2, and R2. This is the only complete circuit in this monstrosity, and the only path through which current will flow. If you look at how E1 and E2's polarities are assigned, they seem to be aiding each other. As such, conventional current will flow in this direction and induce a voltage drop across R1 and R2 with the indicated polarity. Now we can start at any point in this loop and perform a KVL analysis traveling in the direction of induced conventional current. Let's start right here at node D. We go through E1 minus to plus, therefore it is a rise and it goes on the left-hand side of our equation. Now we go through R1 plus to minus, therefore it is a drop, and it goes on the right-hand side of our equation. We now go through E2 minus to plus, therefore it is a rise, and it goes on the left-hand side of our equation. Finally, we go through R2 plus to minus, therefore it is a drop, and it goes on the right-hand side of our equation. Our KVL loop equation for the loop composed of D, A, B, C, and returning back to D is E1 plus E2 equals V1 plus V2. Substituting the given values for E1 and E2 into our KVL equation, 15 plus 25, we find that V1 plus V2 is 40 volts. Given that the values of R1 and R2 are known quantities, we can now easily use Ohm's law, or the voltage divider rule if you're familiar with this method, to determine the voltage drop across each individual resistor. The series combination of R1 and R2 yields a total resistance of RT equals R1 plus R2, 600 ohms plus 200 ohms, or 800 ohms. In its most basic configuration, this single loop could be conceptualized as a single 40-volt source in a circuit with an 800 ohm resistor. I know this is not how our monstrosity is set up, but our KVL analysis allows us to make this simplification. We can now perform an easy Ohm's law analysis of this simple circuit as if this was true. The current through this idealized total resistance is the voltage divided by total resistance. 40 volts divided by 800 ohms yields a current of 50 milliamperes. Given this is a series relationship where the total resistance of 800 ohms represents the series combination of a 600 ohm resistor and a 200 ohm resistor, it can be said that this same 50 milliamperes is traveling both through a 200 ohm and a 600 ohm resistor. Therefore, the voltage drop across each resistor is the current through it times its resistance. V1 equals I1 times R1, 50 milliamperes times 600 ohms, yields a voltage drop of 30 volts. V2 equals 50 milliamperes times 200 ohms, or 10 volts. We've placed these calculated voltage drops inside our redrawn circuit, and now we can use these values to determine the unknown voltages VAE and VCF using two separate iterations of KVL through loops that do not carry current. Despite there being no physical closure to these loops, one can still apply KVL to open circuits, like open switches, or between any 2 points with a voltage differential between them. Again, voltage is a 2-point measurement, and the differential can exist between 2 points with or without the existence of a physically closed path. To solve for the unknown voltage drop VAE with the indicated polarity, we can use a loop of which VAE is part. I can randomly start here at node E and travel in the counterclockwise direction to return to E. We go through E4 minus to plus, therefore it is a rise and it goes on the left-hand side of the equation. We go through E1 minus to plus, therefore it is a rise and it goes on the left-hand side of the equation. Finally, we go through VAE plus to minus, therefore it is a drop and goes on the right-hand side of the equation. This yields the KVL equation E4 plus E1 equals VAE. Substituting in the known values of E4 and E1, we find that VAE equals 39 volts. This makes perfect sense because if you think about it using another redrawn circuit, E1 is just sitting on top of E4's head in a clearly series aiding arrangement, where E1's negative terminal is connected to E4's positive terminal, and we're just asked to find the open circuit voltage of a 15-volt source aiding a 24-volt source, and the answer is obviously 39 volts. Despite there being no physically closed path, there is a voltage differential between these 2 points, and Kirchhoffs' voltage law can be applied. To solve for our last unknown voltage of VCF, we need to use another loop. Again, this is a loop with no physical closure, of which the open circuit voltage, VCF, is part. I'm just going to randomly start here and randomly go counterclockwise. From node D, we go through E3 minus to plus. Therefore, it is a rise, and it goes on the left-hand side of the equation. We then travel through VCF minus to plus. Therefore, it is also a rise, and it also goes on the left-hand side of the equation. Finally, we travel through V2 plus to minus. Therefore, it is a drop, and it goes on the right-hand side of the equation. Our KVL equation for this loop is E3 plus VCF equals V2. Substituting our given quantity of E3 being 12 volts and our calculated voltage drop of 10 volts for V2, we can now solve for VCF by subtracting 12 volts from either side. We find that VCF is negative 2 volts with the indicated polarity. This value is negative because the polarity was initially assigned as such. In reality, node F is actually 2 volts higher than C. And that makes perfect sense. If we're at C and travel through resistor 2, we drop 10 volts to get to node D, and then source E3 brings us back up 12 volts to get to node F. Node F is 2 volts higher than C. However, we were assigned the polarity C2F. So VCF is negative 2 volts. Again, despite there being no physically closed path, there's a voltage differential between these 2 points. See, this complicated monstrosity wasn't nearly as hard as your initial assumptions might have been, because we were organized and consistent in our applications of KVL. I still have no idea what it does. Lest you think we're done with this example, realize there are other loops within this circuit around which we can apply KVL, despite the fact that we've obtained all the required values. Notably here, here, and here. All of these are excellent opportunities to check our work, and you guessed it, give us another opportunity to kick this monstrosity into submission. The KVL analysis of this additional red loop follows: rise E1, fall V1, rise E2, fall VCF, fall E3, and returning to our point of origin. E2 plus E1 equals V1 plus VCF plus E3. If we wanted to check our work for VCF, we can use the given values of E1 and E2 and E3 and the calculated value of V1. 25 plus 15 equals 30 plus VCF plus 12. Subtracting 42 from both sides, we again find VCF with the indicated polarity to be negative 2 volts. If you're looking for more opportunities to perform KVL analysis, by all means, pause the lecture and try the loop in blue and the loop in purple. The KVL equation for the blue loop, regardless of point of origin or direction of travel, will yield the following KVL equation: E2 plus VAE equals E4 plus V1 plus V2. The purple loop, regardless of point of origin or direction of travel, will yield the following KVL equation: E2 plus VAE equals E4 plus V1 plus VCF plus E3. You can use any or all of these KVL loop equations to check one another or Ohm's law calculations. Let's check out a circuit using Kirchhoffs voltage law that does have an identifiable purpose and maybe something you might see one of these days. This is the world's simplest battery charger ever made. Battery chargers are obviously a lot more complex than this, but this will do fine to illustrate the general functionality of a battery charger, introduce a new type of multi-source series circuit, and apply Kirchhoffs voltage law. You'll immediately notice that these two DC sources, if left to their own devices, would induce conventional current in two opposite directions and are no longer aiding one another. In fact, you could say that they are fighting or opposing each other. This is a series opposing configuration, and as the name implies, there is a conflict of polarities and resultant current. As is often the case in conflicts, the strongest decides the outcome. If the source on the left-hand side represents a constant 14.1 volt DC output of a car's alternator, and the source on the right-hand side represents a discharge automotive battery at 11.6 volts, let's investigate three important questions. Which direction will current flow? How much current will flow? And finally, what does the flowing current do in such an arrangement? The answer to the first question is very easy. Conventional current would travel left to right because the strongest source is on the left-hand side, and the strongest source in this opposing relationship dictates the direction of current flow. Given conventional current flows from left to right, the adjustable resistor between these two series opposing sources would have a voltage drop with the indicated polarity. The answer to the second question requires a KVL analysis and a known resistance value. Let's say the adjustable resistor was set to 2.5 ohms. Performing a KVL analysis, we can start at the ground node and travel clockwise. We rise E1. We fall VR, the voltage drop across our adjustable resistor, and then fall E2. Our KVL equation for this loop is E1 equals VR plus E2. Substituting in the known values for E1 and E2 and subtracting 11.6 from both sides, we find the voltage drop across our adjustable resistor is 2.5 volts. Visually, you can think of the KVL loop this way. Start at ground. Take one end of the adjustable resistor and bring it up 14.1 volts. Now start at ground and take the other end of the adjustable resistor and go up 11.6 volts. What is the voltage differential across our adjustable resistor? It's obviously 2.5 volts. Either way, Ohm's law states that the current through a 2.5 ohm resistor exhibiting a 2.5 volt drop is 1 amp, traveling in the indicated direction. Yet another, more advanced way to think about this is to envision both sources independently acting upon the single adjustable resistor, and their individual effects are superimposed upon each other. You'll notice I often use dramatic pauses and emphatic pronunciation to foreshadow things you'll be seeing in the future. There is no doubt that a 14.1 volt source opposed by 2.5 ohms of resistance would induce 5.64 amps clockwise, and an 11.6 volt source opposed by 2.5 ohms of resistance would induce conventional current of 4.64 amps flowing in the counterclockwise direction. Pause the lecture to check my work, I dare you. However, if both were simultaneously pushing their respective current amounts in their respective directions, the result would only be 1 amp clockwise. It's like two rivers colliding, where both are flowing, but one clearly overwhelms the other. If you were sitting on the bank, you'd count only 1 amp of current pass you by left to right through our adjustable resistor. This is the superposition theorem, and we'll get to it a little later in our discussion of DC network theorems. It's one of my favorite theorems because it's so simple and makes so much intuitive sense. Finally, let's answer our last question. What does flowing current do? This is $1 million question. It has nothing to do with KVL, but everything to do with batteries. In its simplest terms, the current is being forced backwards through the battery on the right and reversing the chemical reaction that initially discharged it. We'll get to some of the electrical details of batteries in later lectures, but for now, realize when you send current into a battery, you charge it up. Keep in mind this current must be controlled and of the correct magnitude and duration for this to be efficient, effective, and most importantly, safe. Which brings us back to our adjustable resistor. This is the means we use to control current and safely, efficiently, and effectively control the charging process. If this second battery is now charging, over time we should see this voltage value gradually rise. Let's say after 10 minutes we check, and this second battery is at 12.1 volts. The figures inside our previous KVL analysis no longer apply because E2 has changed magnitude. Our new KVL equation is as such: 14.1 equals VR plus 12.1. Subtracting 12.1 from both sides, we find VR to be only 2 volts. And given the voltage across the adjustable resistor has decreased, yet the resistance has stayed constant, we should obviously expect current to decrease. Given a 2 volt drop across a 2.5 ohm resistor, we can use Ohm's law to determine the current draw. Current is equal to voltage divided by resistance, 2 volts divided by 2.5 ohms, yields 800 milliamperes or 0.8 amps. Let's say, however, that this battery manufacturer recommends an initial constant current charge rate of 1 amp be maintained for a certain period of time. How can we use our adjustable resistor to efficiently, effectively, and safely charge this battery obeying the manufacturer's recommendations? The answer, quite obviously, is if we want to increase the current draw to 1 amp, we need to dial the resistance downwards, in this case to 2 ohms. With a 2 volt drop across a 2 ohm resistor, the current draw is again returned to 1 amp as per manufacturer recommendations. We can do this adjustment at several different points within this battery's charge cycle. As the second battery's voltage increases, the voltage differential across the adjustable resistor drops and drops, and we can progressively open up the tap wider and wider by decreasing the adjustable resistor to allow that continual 1 amp of current into the device. Finally, the device will charge up to 14.1 volts. At this point, current flow will cease to be exchanged between the sources because there is no voltage differential. With 14.1 volts on one side of the adjustable resistor and 14.1 volts on the other, there is no differential and no current will flow. This is a great time to highlight some of the really crazy properties about voltage differentials. Not that I'm recommending you verify this, but if you were to place a conductor, let's say your lab partner, across the terminals of 2 devices, each independently at incredibly high voltage with reference to ground, but equal and identical to each other, there would be no potential difference across this conductor, provided no other part of their body touched anything connected to the ground reference. If, however, a part of their body touched the ground, it would be an extremely shocking experience. Now that we've had an initial discussion about series opposing sources, let me bring to your attention this extremely poor idea. Here are 2 voltage sources of different magnitudes hooked together in a circuit with no means of current control between them. Notice the conspicuous absence of an adjustable resistor or your lab partner strung between the 2 sources. At first glance, this looks to be a clear violation of KVL, because it is a rise of 24 volts and a fall of 12 volts. 24 does not equal 12. What is missing in our schematic is the real-world resistance of the wires forming the connection between the sources. Ordinarily, this resistance is beneath our level of concern and is purposely ignored. In this case, however, this tiny resistance is the only opposition to this differential, in this case 12 volts. I'll redraw the diagram to include the resistance of the conductors between the 2 sources and use this tiny resistance value and resultant current draw to illustrate how incredibly dangerous this configuration is. Let's say our wire is now modeled as a resistor with a magnitude of 100 milliohms or 0.1 ohms. Our KVL analysis of this configuration is rise E1, fall VR, fall E2. Substituting in the known values of E1 and E2 and subtracting 12 volts from each side, we find the differential across this tiny resistor to be 12 volts. With 12 volts across a 0.1 ohm resistor, Ohm's law states that the current through it is proportional to the voltage across it and inversely proportional to the resistance. You can see where this is going, don't you? 12 volts divided by 0.1 ohms yields an expected current draw of 120 amps. OMG, that's huge, and you are going to damage one or both batteries, not to mention make that wire light up like a Kiss concert, because a 0.1 ohm resistor carrying 120 amps of current is dissipating 1,440 watts of power, close to 2 horsepower, about 2 common household toasters. What this goes to show is that a fundamental understanding of KVL illustrates that voltage sources of different magnitudes in parallel are to be avoided at all costs. The only time voltage sources are ever placed in parallel is if they are the exact same magnitude. Any differential will cause the larger voltage source to discharge into the smaller source until the differential between them is exhausted, potentially with damaging results and an extremely high current flow. KVL still applies in these series opposing configurations, even if the resistance between the sources is incredibly small. Another situation seemingly made for KVL is what I call the missing pieces puzzle. Let's say you only have partial information about a series network. In this case, we know the source voltage E to be 24 volts and can read the resistance values of two resistors, in this case R2 at 200 ohms and R3 at 600 ohms. And we can measure the voltage drop across the unknown resistor R1 to be 4 volts. We're being asked to solve for V2 and V3, respectively the voltage drop across R2 and R3, the current through each element, and the unknown resistance R1. Those with only a superficial understanding of series circuits are immediately repelled by the first obstacle they encounter, because they are often reliant upon calculating the total resistance, being the summation of R1, R2, and R3, and then using this value to calculate source current, being the source voltage divided by total resistance. With an unknown R1 value, one cannot solve for total resistance. Without total resistance, one cannot solve for source current. One can, however, use Kirchhoffs' voltage law to determine the voltage drop across the remaining two resistors. Let's perform a KVL analysis of this circuit, starting here and traveling in the clockwise direction. Pause the lecture and take your best shot at this. Rise E, fall V1, fall V2, fall V3. No big surprise there. Substituting in the given values of E and V1 and subtracting 4 from both sides, we find the voltage drop across the remaining two resistors to be 20 volts. There are several methods to proceed from this point, the simplest being a visualization of just R2 and R3 in a series configuration with a 20 volt source. This should be absolute child's play to anyone familiar with Ohm's law and series circuit properties when asked to solve for the voltage drop across and the current through each element. What may not be so evident is that conclusions from this simplification can then be applied to our original circuit and then used to solve for the desired unknowns. Another alternative visualization method is to zoom in on a secondary loop formed by two resistors R2 and R3 and the 20 volt drop across them obtained from our previous whole series circuit KVL analysis. Again, loops scribed by KVL needn't be physically closed loops as illustrated previously. Starting here, we rise 20 volts. We fall V2 and fall V3, again yielding the same results as our two-element simplification. In both cases, the voltage drop across an element is the current through it times its resistance. V2 equals I2 times R2, and V3 equals I3 times R3. Substituting into our KVL equation, we find 20 equals I2 R2 plus I3 R3. And understanding that this is a series configuration, we realize I2 equals I3, and for that matter, equals I1 equals IS. We can substitute this into the equation and factor out our like term IS. We find 20 equals IS times parentheses R2 plus R3 close parentheses. Substituting in the known values of R2 and R3, 200 ohms and 600 ohms, and solving for current, we find source current equal to 20 volts divided by 800 ohms, or 25 milliamperes. With 25 milliamperes traveling through a 200 ohm resistor, V2 is 5 volts. Similarly, we could use Ohm's law to solve for the voltage drop V3. However, since this lecture is entitled Basic Kirchhoffs Voltage Law and not repetitive use of previously covered material, we can use KVL to solve for V3. Given E equals V1 plus V2 plus V3, we can substitute in the given value of E, V1, and our calculated value of V2 into the equation. We find 24 equals 9 plus V3. Subtracting 9 from both sides yields V3 equals 15 volts. However, being rightly skeptical of such an easily obtained voltage drop, we can use Ohm's law to check this value. With 25 milliamperes traveling through a 600 ohm resistor, we would expect a 15 volt drop. Oh my gosh, it's what we just solved using Kirchhoffs' voltage law. The only task remaining us is to solve for R1. Given that we know the voltage drop across it and the current through it, we can use Ohm's law to solve for R1, where R1 equals V1 divided by I1, 4 volts divided by 25 milliamperes, yields 160 ohms. Or we could use the series resistance summation formula to solve for the unknown R1, given our 24 volt source is inducing 25 milliamperes of current through this 3-element network, where RT equals our source voltage E divided by our source current IS. 24 volts divided by 25 milliamperes yields a total resistance of 960 ohms. If RT equals R1 plus R2 plus R3, substituting in the given and the calculated values, we again find R1 to be 160 ohms. We can finally perform a sanity check of our results using KVL, where our voltage rise is dissipated by the sum of drops. E equals V1 plus V2 plus V3. Does 24 equal 4 plus 5 plus 15? Yes, indeed it does, and we can be reasonably certain we've obtained the correct results. In addition to its application as an active analysis technique and sanity check, KVL is an extremely handy and powerful troubleshooting technique in lab and in the field. Imagine, if you will, arriving at lab ever so slightly late. All the desirable lab partners have drifted off to their respective stations and are judiciously following directions, performing required calculations, and dutifully and carefully assembling their circuits. You have the misfortune of being partnered up with one of those people that wears a baseball hat sideways. You know, a person of such dubious intelligence, they're more properly considered lab obstacles rather than lab partners. Sideways Hat has taken it upon themselves to build something they swear is the circuit you're supposed to be working on. None of their valid observations, I'm making quotation marks with my fingers by the way, make sense and seemingly violate KVL. This is the time for you to realize this simple and powerful fact. KVL cannot be disobeyed. It goes to work every day, just like gravity, and continues to work long after you've given up on your lab partner and gone home to punch the next person you see wearing a baseball hat sideways. Reality cannot disobey KVL, and it's up to you to interpret the values you're observing with that in mind. Consider the following circuit and the following scenarios that could make it all go wrong. This ain't your first rodeo, so you've done your pre-lab homework and performed the necessary calculations prior to even thinking about touching a piece of equipment. Again, this is the point of calculations. Don't show up to a gunfight carrying a knife. Building circuits and taking observations is utterly meaningless if you don't know what to expect. I swear, this is the one thing I'm going to be on your case about for the remainder of our time together. If there is one troubleshooting tip I can give you that is worth more than 1,000 other tips combined, it is this single rhetorical question. How is it supposed to work? A rhetorical question, by the way, is a figure of speech in the form of a question that is asked in order to make a point, rather to elicit an answer. I know how it's supposed to work. Do you? Again, another rhetorical question. My intention in asking this over and over is to provoke thought on your part and insinuate that the answer is right in front of you, given your previously acquired skill set. In this spirit, you are on your own. Pause the lecture and see if you can perform an analysis of this circuit to solve for the expected voltage drops across these two series resistive elements, supplied by a 16-volt source. Here's the challenge though. You are only allowed to use Ohm's law twice. Take your best shot. You've only got two, so aim well. The total resistance seen by this source is RT equals R1 plus R2. 300 ohms plus 200 ohms yields a total resistance of 500 ohms. The source current produced is equal to the source voltage divided by total resistance. 16 volts divided by 500 ohms yields a current of 32 milliamperes. This is the first time we used Ohm's law. Given current through elements hooked in series is the same, it can be said that the current through R1 is also 32 milliamperes. The voltage drop across element 1 is the current through it times its resistance. 32 milliamperes times 300 ohms yields a voltage drop of 9.6 volts. This is the second and last time we're allowed to use Ohm's law. However, we've yet to solve for the voltage drop across R2. Without Ohm's law, we're seemingly backed into an alley, painted into a corner, up the creek without a paddle, or any other analogy befitting a hopeless situation. Fear not though. Luckily, you're allotted limitless use of KVL. There's a rise of E, a fall of V1, and a fall of V2. Substituting in the given value of E and the calculated value of V1 and subtracting 9.6 volts from either side, we find V2 equals 6.4 volts. 2 Ohm's law jabs and a KVL uppercut, and this circuit is KO'd. As a tantalizing preview to those individuals yet to learn the voltage divider rule, I'll soon show you how to perform this same analysis with no usage of Ohm's law, but rather a trick most cunning that cuts out the busy work and boring repetition. Regardless, we are now armed with a truth that for some reason, your lab partner is incapable of demonstrating. Consider this scenario in which the voltage drop across R1 is observed to be 16 volts. Hold everything. Be neither cruel nor forgiving to your lab partner. Be honest, objective, and forthright. This is not the circuit you're supposed to be working on, but rather some other creative, i.e. totally wrong, interpretation of it. Given an observed voltage drop of 16 volts across R1 and an expected voltage drop across R2 of 6.4 volts, we are in clear violation of KVL, because 16 volts does not, nor ever, equal 16 plus 6.4, or 22.4 volts. What is your instinctual response to this situation? Pause the lecture if you want to and think about this. What is your next step? I'd love to say in a gentle and reassuring tone, relax, don't worry about it. Remember, there are no wrong answers. But I won't, because there are wrong answers. Right answers, totally wrong answers, and answers that serve no purpose but to check things that aren't broken. A valid answer to this question is as such. Check the supply voltage. If the supply voltage is not 16 volts as required, but rather something higher than 16 volts, it would be understandable that R1 would drop more voltage than expected because it's not the circuit you intended to build. Before we move on to any additionally valid answers to this quandary, pause momentarily to consider the magnitude of the source voltage necessary to induce a 16-volt drop across a 300 ohm resistor in series with a 200 ohm resistor. Again, this hypothetical scenario is an excellent opportunity for you to apply Ohm's law, basic series circuit properties, and KVL. Pause the lecture if you want to take a stab at this. If you're correct, you should find a source voltage of approximately 26.7 volts would do the trick. 16 volts being dropped across the 300 ohm resistor and 10.7 volts being dropped across the 200 ohm resistor. Let's give our lab partner a little credit though. Setting up the supply voltage should be easy, as should be ensuring the correct components are being used, as well as instrumentation being employed properly. Let's assume they're not a total doof and are just having troubles building the circuit. These assumptions being made, an equally valid answer to this same question is also this. Check the voltage drop across R2. Here's where we must necessarily place a fork in the road. What if your subsequent check of the voltage drop across R2 yielded 0 volts? What if your subsequent check of the voltage drop across R2 yielded 16 volts? These are two totally different, totally wrong creative interpretations of the circuit you're intending to build. Dealing with the first scenario, we find a circuit exhibiting all voltage drop across one resistor and none across the second. This being said, the circuit is clearly in obedience to KVL in that a 16 volt rise equals a 16 volt fall plus a 0 volt fall. Let that at least be a small comfort to your softly weeping lab partner. Given your understanding of Ohm's law, you are undoubtedly familiar that the voltage drop across an element is proportional to the current through it times its resistance. V2 equals I2 times R2. If there is no current flowing through the second resistor, there will be no voltage drop across it. Situations that might cause such observable misbehavior might be simply failing to include R2 in the circuit by having one or both terminals just dangling out in space, or shorting out R2 with a low resistance path via an improper connection or improper placement on a protoboard. Improper placement on a protoboard is the number one error I've observed in a lab environment. Actually, this is the number 2 error, because the first error is wearing a baseball hat sideways. A resistor with both terminals placed into a single node that is electrically connected via a 0 ohm conductive clip, not visible to the naked eye, but easily recognizable to those that know how to use an ohm meter in a protoboard, presents no resistance from terminal to terminal. This resistor is shorted out via the conductive clip. In effect, this conductive clip connecting columns A through E, or F through J, inside individual rows on a protoboard, acts like a low resistance path placed in parallel to the resistor in question. Anything placed in parallel with such a low resistance path presents no opposition to current flow and effectively removes this resistor from consideration. In this case, the source is only seeing R1's opposition, and all voltage will be dropped across it. I must reiterate, components go node to node on a protoboard, and at no point would I ever place 2 leads of a component at the same node. It doesn't make sense schematically, nor does it make sense when looking at a protoboard at the nodal level. If you've got circuit building issues using a protoboard, by all means, check out the Lab Practices Intro to Protoboards lecture, available at the Big Bad Tech channel, and just get in the driver's seat and start building circuits on a protoboard. You can't learn how to ride a bike if you don't ride a bike. Yes, your first couple rides will result in a crash. Provided you're not hopelessly mangled, pick yourself up, dust yourself off, and get back on the bike. Close visual inspection of the as-built circuit will quickly indicate which error is present. Only in sheer desperation would you ever resort to additional instrumentation, such as an ammeter used to measure current through R1 or R2. Again, use your senses to find the error, and only in extreme scenarios would you ever use instrumentation to extend the reach of your senses. Dealing with our second scenario, in which V2 is also exhibiting a 16-volt drop, we find a circuit seemingly in violation of KVL, and that our 16-volt rise does not, nor ever will, equal a 16 plus 16-volt fall. There is not a contradiction between your observations and your expectations. The contradiction rather lies in that you are observing values for a totally different, i.e. totally incorrect circuit. Consider this arrangement of not R1 and R2 in series with one another, but rather in parallel. In this circuit, there exists only 2 nodes, and both resistors and the voltage source are strung between them. Given the source provides a 16-volt rise from node to node, it is easily noted that there exists a 16-volt drop when you complete the loop. And here is where it gets interesting. Regardless of which loop you travel, R1 has a 16-volt drop, as does R2. Pause to consider the ramifications of this simple observation. Elements hooked in parallel always have the same voltage across them. This may not seem relevant now since we're dealing with primarily series circuits, but realize I just tricked you into learning the fundamental property of parallel circuits using a technique you should, by now, be intimately familiar with, notably KVL. Allow me to elucidate 2 very important electrical properties. Dramatic pause. Elements in series must carry the same current. Elements in parallel must have the same voltage across. I will spend the remainder of this playlist and others hammering these 2 points over and over from numerous different hammering angles. I will never bait and switch you, nor backtrack these 2 very important and very useful observations. Elements in series must carry the same current. Elements in parallel must have the same voltage across them. I now return you to your regularly scheduled lecture on KVL. This being said, this is not the circuit you intended to build. It's wrong and must be rebuilt as required. The point is, at no time did reality disobey KVL, but rather not only has your lab partner failed to do the calculations as required, they've also failed to carefully and judiciously build the circuit as intended. Keep in mind there is no limit to the bad things that can and will go wrong. Let's consider another troubleshooting scenario in which no voltage drop across either element is observed. V1 equals 0 volts, V2 equals 0 volts. Let's again assume the voltage source is at 16 volts and is turned on. There is undoubtedly a 16 volt rise in our circuit, yet for some reason neither element drops any portion of this rise. The voltage drop must occur somewhere else. Via Kirchhoffs' voltage law, we're just not seeing it. Pause the lecture and think about this. What might cause an element in a series relationship to exhibit no voltage drop? Additionally, what would your next step be in troubleshooting such a scenario? Recall, the fundamental shared property of series circuits is that of current. If there exists a break or open in a pure series circuit, no current can flow through it. With no current flowing through any element, Ohm's law states that no voltage drop will appear across any element. There is no current in our series circuit. An ammeter placed in series with this circuit would indicate the existence of no current through this circuit. However, would not necessarily be of any use in pinpointing the error. Visual inspection of the circuit might yield a faulty connection or errant wire. However, let's see if we can use our voltmeter and Kirchhoffs' voltage law to pinpoint the error via comparison of our expected and observed properties. If there exists a voltage rise, there also exists a voltage drop. Where the drop occurs is across the open. Note our initial schematic shows the source in series with two elements, necessitating three nodes, A, B, and C. V1, using double subscript notation, can be rightly called VAB, and V2 can be called VBC. Obviously, VAC should be 16 volts. And our calculations indicate VAB should be equal to 9.6 volts, and VBC should be equal to 6.4 volts. Now, pause to consider the voltage at node A with reference to node A, the voltage at node B with reference to node B, and the voltage at node C with reference to C. This may sound stupid because voltage is a two-point measurement, and obviously all three of these, in effect, single-point voltage measurements should be 0 volts. True, this is what you'd expect. However, all bets are off because our observations aren't matching our expectations, and there is an open somewhere in our circuit. Consider the following scenario in which VAB equals 0 volts, as does VBC. However, there exists a 16 volt drop between the two terminals of our resistors. We're using our voltmeter to measure VBB on our schematic. Ordinarily, we'd expect to observe 0 volts because B is supposed to be a single node, but it's not. We've discovered an errant open between two nodes. The additional one I'll call B prime. Let's redraw the circuit to clearly indicate what is happening. There exists an open in our circuit between B and B prime. No current can flow through this open, therefore no current can flow through either element in this series relationship. Therefore V1, or VAB if you prefer, is 0 volts, as is VB prime C. Performing a KVL analysis, we rise E, fall VAB, fall VB B prime, fall VB prime C. Substituting in our given and calculated values, we find VB B prime equals 16 volts. It's very easy to see that the open circuit VB B prime is the only voltage drop in this circuit, and it is equal in magnitude to the rise. Another visual means of describing this is to start at the negative terminal of our source. Go up 16 volts. Drop 0 volts across R1, meaning that the B node is still at 16 volts. Drop 16 volts, meaning that the B prime node is at 0 volts. Drop 0 volts across R2 and return to the source negative terminal. What this means is that both node A and B are charged up to 16 volts. And the reason the voltmeter reads 0 volts when measuring the voltage drop from A to B is that there is no difference between A and B. Similarly, node B prime and C are both at 0 volts. And a voltmeter reading V prime C would measure no differential between B prime and C. Yes, in a properly constructed circuit, there will be a path for current flow, and there will be a voltage drop across R1. That is clearly not the case with an open in our circuit. This is a little hard for beginning electronic students to understand, but an element touching a voltage source's terminal will assume that terminal's potential at all points within it if there is no path to the other terminal. The only thing preventing a voltage drop is current flow. When current equals 0, IR drops, or voltage drops equal 0. The only thing preventing current flow is the open circuit, and therefore the voltage drop will occur across the open circuit. KVL explicitly states this, as does playing loosely with a couple useful series circuit properties. Recall that the largest voltage drop in a series relationship always occurs across the largest resistor in that path. The resistance of an open circuit is infinite, and it can't get much larger than infinite. Therefore, all voltage will be dropped across this infinitely large resistor. Pause to consider opens at nodes A or node C. In both scenarios, no voltage drop will occur across R1 or R2 because no current will flow through either element. The voltage drop will always occur across the open. In the case of an open at node A, I have to introduce an additional node I'll call A prime. The 16-volt drop occurs between A and A prime, meaning that node A prime, B, and C are all at 0 volts, and there is no voltage differential across our two resistive elements. In the case of an open at node C, I have to introduce an additional node I'll call C prime. The 16-volt drop occurs between node C and C prime, meaning that node A, B, and C are all at 16 volts, and C prime is at 0 volts. A, B, and C all being at 16 volts means there is no differential between them. Again, voltage is a two-point measurement of differential. The differential occurs across the open. This again goes to show you that even circuits without closed paths allowing current flow obey Kirchhoffs' voltage law. Keep in mind there is no limit to the wrong an unsupervised lab partner can wreak upon your lab. But let these short examples stimulate your thinking how properties like KVL can be used to detect and rectify such errors. The moral of the story? Show up to lab early, you get your first pick of lab partners. Alright, we are just about to wrap up our discussion of KVL, but before we do, allow me to apply this concept to scenarios involving semiconductor devices and motors. At first glance, these may seem impossibly complex, but realize they are just exceedingly simple applications of KVL using different devices. Our first circuit consists of a series arrangement of a 5-volt source, a diode, and a 200 ohm resistor. Although I've incorporated diodes in previous lectures, I've shied away from detailed discussions about how they work, only telling you to ignore them or dismissing them as nonlinear devices. Here's the deal. You don't need to know how they work internally at this point in your career. We'll deal with semiconductor devices and circuits and power electronics in much later lectures. But for right now, all you need to know about diodes is this. They are electrical check valves, in that they do not allow current flow in one direction and do allow it in the other. When reversed biased, i.e., when conventional current is trying to flow counter to the arrow indicated on the schematic, they are an open circuit and no current can flow through the diode. If there is no current flow through the diode, there is no voltage drop across the resistor. Where does the voltage drop occur? Obviously, the 5-volt voltage drop will occur across the open, in this case, the reversed biased diode. This all changes, however, when I flip the diode so it is now forward biased. A forward biased diode allows conventional current to flow in the direction indicated by the arrow on the schematic symbol. Here's the tricky part though. When conducting in the forward bias mode, there's a small voltage drop across the diode with the indicated polarity. In this case, we're going to assume that this voltage drop is 0.7 volts. Perform a KVL analysis of this circuit. Determine the voltage drop across the resistor and the current through the circuit. Pause the lecture and take your best shot. I'm going to start here and travel in the direction of conventional current. There is a rise of E, a drop across the diode, and a drop across the resistor. Substituting in the given values, we find the voltage drop across the resistor is 4.3 volts. Ohm's law states that the current through this resistor is the voltage drop across it divided by its resistance. 4.3 volts divided by 200 ohms yields a current of 21.5 milliamperes. Too easy. Even though we're using devices typically reserved for discussion in second-year electronics engineering technician classes, we're still already capable of solving these types of problems using basic electronic principles like KVL. Keep in mind the diode comes in all types of flavors, including silicon, germanium, and light-emitting varieties. Don't assume this 0.7 volt drop when in the forward bias mode is universal. For example, consider an LED, a light-emitting diode. Let's say it's a soothing green color that drops 1.8 volts when conducting in the forward bias mode. Notice I swap locations of the diode and the current controlling resistor. You can do this. Current and series relationships is the same. Determine the resistance value necessary to limit this current to 24 milliamperes. Pause the lecture and take your best shot at this. Not only is this another chance to practice KVL, it's a synthesis of this topic with basic Ohm's law and series circuit properties. Again, I'm asking you to determine the resistance necessary to limit the current through the diode to 24 milliamperes. Regardless of the value of the resistor, because of the nonlinear nature of the diode, there will be the same voltage drop across it. The voltage drop across the resistor can be easily determined via KVL. Let's start here and travel in the direction of induced conventional current. We rise our source, fall VR, fall VD. Substituting in the given values and subtracting 1.8 volts from both sides, we find the voltage across our resistor to be 3.2 volts with the indicated polarity. With a 3.2 volt drop across this resistor, what is the resistance necessary to limit current to 24 milliamperes? Ohm's law states that resistance is equal to voltage divided by current. 3.2 volts divided by 24 milliamperes yields approximately 133 ohms. Again, this seemingly advanced problem is just a simple application of KVL. Finally, let's consider a DC motor. In this case, I've drawn a simplified schematic for the field and armature windings of a separately excited DC motor. Again, you may not know what an armature is, nor a field, nor even a DC motor, but realize the observable effects of current draw for this motor is easily explained using KVL. A separately excited DC motor, as the name implies, uses two separate sources to supply current to the field and the armature windings. The field winding is the stationary part of the motor, and the armature is the rotating part. The windings are modeled as resistors in this schematic. When energized, there is a large current draw by the armature because the resistance is so low when the motor is at rest. This phenomenon is known as inrush. At rest, the full 120 volts is applied across this 7 ohm modeled armature resistance. The current draw by the armature is the armature voltage divided by armature resistance. 120 volts divided by 7 ohms yields a current draw of approximately 17 amps. Yowza, what a rush. A locked rotor condition, one in which the motor shaft isn't spinning due to application of too much load torque, is clearly something to be avoided for any considerable length of time because of such a large current draw. However, a spinning armature exhibits another phenomenon known as counter-electromotive force, sometimes known as CEMF, due to the generating aspects of moving a conductor through a magnetic field. Again, you need not worry about the nitnoid details of this phenomenon if you can understand this model. Counter-electromotive force is represented as a series opposing voltage source. Let's say at rated speed, this motor produces 80 volts of CEMF. This 80 volts of CEMF pushes back on the armature supply voltage. We need to apply Kirchhoffs' voltage law. Let's start here and travel in the indicated direction. We have a rise of our supply voltage to our armature. we have a voltage drop across the resistance of our armature and a voltage drop of our counter-electromotive force. Substituting the given values, we find the voltage drop across the resistance of the armature to be only 40 volts. We find the current draw to be equal to the voltage drop across the resistance of the armature divided by the resistance of the armature. 40 volts divided by 7 ohms yields a substantially reduced current draw of approximately 5.7 amps. Yet again, another customarily advanced topic felled with a swift and devastating KVL kick to the... Use your imagination. Let this preview be an advanced warning to those that plan on completing the DC circuit analysis, AC circuit analysis, three-phase AC circuit analysis, motors and generators, motor controls, power electronics, or any other of the upcoming playlists at the Big Bad Tech channel. This is not the last time you will see and use KVL. KVL is now a tool I expect you to keep sharp and always ready. All right, we have got to wrap this up. The section might be a little long, but trust me, it was worth it. KVL is a very useful circuit analysis technique, and like I said, you will be using it again and again. In conclusion, this lecture took a look at Kirchhoffs' voltage law and used it to analyze, verify calculations, and troubleshoot simple series DC circuits, as well as some customarily more advanced ones. Remember to review this concept and practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.